Welcome to my YouTube channel. Today I will solve some important questions. So first example, given that z plus 2y equal to iz plus k belongs to R, and this also are given, that is w divided by z equal to 2 plus 2y and imaginary w equal to 8. So we have to find the value of k. So from this we get z minus iz equal to k minus 2y. So z equal to k minus 2y divided by 1 minus I, and here w equal to z is given that 2 plus 2y. So w can be written as 2 plus 2y into z, and if we put the value of z we get k minus 2y, and here 2 plus 2y divided by 1 minus I. By multiplying complex conjugate, that is 1 plus I, and here 1 plus I, so we get k minus 2y, and here this becomes 2 into 1 plus I, that is whole square, and here we get 1 minus I square, that is 1. So 1 plus 1, so this is 2, so this cancel out, and this is 1 plus I square, that is k minus 2I, and this is 1 plus I square, that is 1 plus 2y plus I square, that is minus 1, that is minus 1 cancel out, so we get 2y into k minus 2y, that is k 2ki minus 2y 4 I square, that is plus 4. So as this is given that imaginary, so this is w, so w equal to, we get this, and this is given that imaginary w equal to 8. So here, from here we get imaginary w, that is 2k, so 2k equal to 8, this gives, and k equal to 4. So this is the final answer, k equal to 4. You can note down. First we find the value of z from this given equation, and the value of z we put here, and from this we get w, and as this imaginary w equal to 8 is given, so from here 2k equal to 8, so k equal to 4. This is the example 2, given that z equal to cos theta plus I sin theta, where theta is belongs to 0, between 0 and 2 pi, and we have to show that 2 by 1 plus z equal to 1 minus I tan theta by 2. So we take left hand side and we prove that this is equal to this. So left hand side 2 divided by 1 plus z, and z is given, so we put the value of z, that is cos theta plus I sin theta. So now this is the real part and this is the complex part. So by multiplying complex conjugate, that is 1 plus cos theta minus I sin theta, and this is 1 plus cos theta plus this, and also the I sin theta, this is, and this is 1 plus cos theta minus I sin theta. So from this we can write, this is unchanged, cos theta minus I sin theta, and this will be a plus b into a minus b, that is a square minus b square, that is 1 plus cos theta whole square plus b square, that is I square sin square theta, a square minus b square, that is minus I square sin square theta, as I square equal to minus 1, so this become plus. So from this, if we calculate this, 1 plus 2 cos theta plus cos square theta, and also this is sin square theta. So as cos square theta sin square theta equal to 1, so from this, the denominator we get 2 plus 2 cos theta, and the numerator becomes same. From this we get 2 1 plus cos theta minus I sin theta, and denominator becomes, this is 1 1 2, and there are 2 cos theta, that is 2 common, 1 plus cos theta. 2 to cancel out, and if we can divide by parts, that is this by this, that is 1 plus cos theta divided by 1 plus cos theta, and this is minus I, and here sin theta divided by 1 plus cos theta. So this is 1 minus I. Sin theta can be written as 2 sin theta by 2 cos theta by 2, and this can be written as 2 cos square theta by 2, as cos 2a equal to 2 cos square a minus 1. So this can be 1 plus cos 2a equal to 2 cos square a. So 1 cos theta can be written as 1 plus cos 2 into theta by 2, and then we apply this formula, can be written as equal to 2 cos square theta by 2. So this can be written as 2 cos square theta. So now 2 to cancel out and 1 cos theta by 2 cancel out. So 1 minus I, this is sin theta by 2, and this is cos theta by 2. That is 10 theta by 2. So this is right hand side. So proved. This was the second example. You can note. Now I will discuss the third example. Solve this question. Example 3. Given that z equal to a plus ib divided by a minus ib, where ab belongs to r. So we have to show that z square plus 1 by 2z equal to a square minus b square divided by a square plus b square. Let us take left hand side. So this is z square plus 1 divided by 2z. So simply we put the value of z, that is a plus ib, a minus ib, that is whole square, plus 1 divided by 2 into z, that is a plus ib divided by a minus ib. Simply we multiply both sides by a minus ib whole square, a minus ib whole square. So from here, this is a minus ib whole square plus a minus ib whole square total divided by a minus ib whole square. So 1 a minus ib whole square we cancel. So this becomes a plus ib whole square, and this is a minus ib whole square. And if we calculate here, so 1 a minus ib cancel out with 1. So this becomes 2 into a plus ib, and here it's a minus ib. As we know that x plus y whole square plus x minus y whole square equal to 2 into x square plus y square. So from this we can find this is a, this is x plus y whole square plus x minus y whole square. So this can be written as 2 into a square plus I b whole square, and here this becomes a plus ib, a minus ib, that is a square minus b square. So a square minus I square b square. So this become, this is a square I square, that is minus a square, 2 to cancel out. So a square minus I square is minus 1. So this become minus, and b square, and this will be a square. I square is minus 1. So minus become plus. So this is right hand side, this is right hand side. So simply we prove this. So this is very simple problem. Direct we put here, one calculation is here, that is we multiply both numerator and denominator by a minus ib whole square. So if you calculate this, from this we get total a fraction which contains a plus ib whole square plus a minus ib whole square and divided by a minus ib whole square. So 1 a minus ib whole square cancel out, and from here 1 cancel out and 1 remaining. So this becomes 2 into a minus a plus ib and a minus ib, and we simply apply this formula, and from here a plus b and a minus b becomes a square minus b square. So we write this. So we simply get this. So if you like it, please subscribe my channel. I will cover all the previous year questions.